We are going to continue working on transformations of graphs, and in this particular video, we are going to focus on horizontal translations. So I wanted to take a minute to look at how the equation looks different if the graph is going to be translated vertically or horizontally. So you can see I have the same parent function on the left and the right. Here I have a quadratic, here I have a quadratic. This time the plus 3 is on the inside in the parentheses. This time the plus 3 is on the outside after the squared. And then for my trigonometric graphs, you can see here that I have added a radian measure on the inside or subtracted. And here I have added or subtracted an integer on the outside. So the question is, for one like this with a minus 4, how will you know whether this minus 4 is a vertical or a horizontal translation? Because I'm adding and subtracting for both of those things. Well, the way you're going to be able to tell is based on the location of the number that you have added or subtracted. You can see that all of these on the right-hand side are added or subtracted outside of the function. You square first and then you add 3, or you take the absolute value first and you add 1, or you find the cosine and then you subtract 2. So when the number is on the outside of the parent graph, when it's on the outside of our original function, this is going to be a vertical movement. This is going to translate the graph up or down. But all of these over here, the numbers that I have added or subtracted, they're on the inside of the function. I'm going to add 1 first and then take the square root. I'm going to add pi over 2 to that angle, and then I'm going to find the sine. So when it's on the inside of the function, inside that parent graph, this is going to be a horizontal movement. This is going to move the graph left and right. Okay, so let's see how that works. I've got a couple of cube root graphs here, and I want to figure out which way this plus 1 and minus 2 is going to move the graph. So I'm going to sketch a cube root right here. All right, there's the equation or the graph of a cube root function. And what I want to focus on is the x-intercept. This one happens to have an x-intercept at the origin. It doesn't really matter where your x-intercept is. What just matters is that we're focusing on the x-intercept. And you remember that to find an x-intercept, you put 0 in place of y, and then we're going to solve what we have for x. Okay, so I need to get rid of that cube root. In order to undo a cube root, I'm going to cube both sides. Cube and cube root are going to cancel one another out. And so what's going to happen here on the left-hand side, 0 cubed is 0. On the right-hand side, I'm going to have x plus 1. Okay, so I'm still trying to get x by itself to find that x-intercept. So I'm going to subtract 1 from both sides. Negative 1 equals x. So what happens is because I had to do the opposite right here, I had to do the inverse operation to move it to the other side. Turns out this plus 1 has the effect of moving my x-intercept over here to negative 1, so it will move the entire graph to the left. So when you add a value, that's going to move your graph to the left. Okay, so based on that, what do you think is going to happen when you subtract a value? Okay, let's test your hypothesis. I'm going to put in a 0 for y, and then we're going to solve this for x just like we did before. To get rid of the cube root, I'm going to cube both sides. Cube and cube root cancel one another out. So I'm going to have on the left-hand side, 0 cubed again is 0. On the right-hand side, I have x minus 2. So I'm going to add 2 to both sides. And I get x equals 2, which is going to move that x-intercept from the origin where it really originally was 2 places to the right over here to positive 2. So if you guessed that when you subtract, you move your function to the right, you guessed correctly. Okay, let's look at moving a couple and see what happens. So the first one I have graphed for us here is the absolute value of x. That red graph is just our original parent function. This plus 3 tells me I'm going to shift the entire graph 3 places to the left. So I'm going to take my vertex right here, which would be on the point 0, 0, and I'm going to shift it 3 places to the left, which is going to put it here. And then I'm going to attach the absolute value graph to this point. It's the same shape. I still have that diagonal line up and to the right. I have a diagonal line up and to the left. It's just that my shape has been moved 3 units to the left. So horizontal translation, 3 units left. All right, let's try this one. This time I've got exponential decay. I can tell it's decay because my x value is, my a value, sorry, is in between 0 and 1. Let's change that to an a. And my x is just a plain old x right here. Now this -4, this is inside of the function. So that means it's going to be a horizontal movement. It's subtraction. So that means it's going to move to the right. So just like we talked about before when we did exponential growth in the last video, the two things I'm going to be looking at are my anchor point and my asymptote. Okay, so you remember that the anchor point is at the point 0, 1, because everything raised to the 0 power other than 0 itself is 1. So I'm going to take that anchor point and I'm going to move it 4 places to the right. So it was right here on 0, 1. I'm going to shift it over here to the point 4, 1. I'm going to move it 4 places to the right. Okay, now how about my asymptote? Well, when I move to the right and to the left, that doesn't affect my asymptote at all. I'm just sliding along this asymptote, so I'm not going to move it. I'm just going to hit it a little bit later. So I'm going to take this same shape. I'm going to start way up here. I'm going to come down through my anchor point and then start getting close to my asymptote over there on the right-hand side. So where you can see it's very close to the asymptote over here, now it's not going to get very close until over here. Everything has shifted 4 places to the right as I move across my graph. Okay, let's do a trig one. So I'm going to move the graph of tangent theta pi over 2 units. Should I move it to the left or should I move it to the right? Well, I'm going to move to the left because I'm adding. All right, so what's going to happen is every one of these x-intercepts, you guys can see those were on the integer values of pi, and I'm going to move all of them over pi over 2 units to the left. So we had an asymptote right here at pi over 2. And now instead of having an asymptote, I'm going to have an x-intercept right there in the middle at pi over 2. And then the asymptote that was at pi over 2, well, it's going to move pi over 2 units to the right, or in this case, the left, sorry, and it's going to be over here. So this point moved pi over 2 units to the left. This asymptote that was right here is also going to move pi over 2 units to the left, and it's going to be right here. Okay, now let's move this point. So this point that was on 0 is going to move pi over 2 units to the left. And then the asymptote that was right here at negative pi over 2 is also going to move pi over 2 units to the left. And I'm just going to keep doing that. I'm going to move this point, pi over 2 units to the left. And I'm going to move the asymptote that was right here, pi over 2 units to the left. And I'll keep doing that over here as well. I should have an asymptote right here, and a point, and an asymptote. Now my tangent shape does not change. The only thing that changes is the location where it is. So I'm still going to move up to the asymptote this way and down to the asymptote this way. It's just that now all of my points and all of my asymptotes have shifted pi over 2 radians to the left. So here is my transformed tangent graph. And if you can see, the original tangent graph is red. The blue one is the transformed one, and I've just taken that shape and moved everything to the left pi over 2 units. Okay, let's do cosine. And we are going to move cosine pi units to the right, right? Because it's subtraction, and so I'm going to move to the right. All right, so let's see what's going to happen here. So this point that was right here at 0 is going to move pi units to the right. Well, I can see pi is right here, so I'm going to put it right there. And then this point that was on the axis right here, it is also going to move pi units to the right. Well, if it was at 1 pi over 2 and I add a whole pi, it's going to end up being over here. 1 pi over 2 plus 2 pi over 2 is 3 pi over 2. All right, now this point that's going to move pi units to the right is going to be off the graph. This point that's going to move pi units to the right, that's going to end up being here. And so I'll just keep doing that, making my way around the graph, moving everything pi units to the right. All right, and when I get over to this point, I don't have anything that I can physically see to move, but I know that cosine is periodic, so I know it's just going to keep going in that same fashion. So when I get over there to the left-hand side where I've run out, quote unquote, of things to move, I can know what it looks like based on the fact that it is cyclical, and I can just keep making that same shape. So one thing I think is interesting here, if you look at the blue one that we just did, that is shifted pi radians to the right, it also just looks like we flipped the red one upside down. So both of those would have the same effect. Shifting it pi units to the right and flipping it upside down will end up looking the same.